Okay, so in the previous lecture, we looked at this thing called the area problem, and that was the problem of finding the area below a certain function, or the graph of that function, and above the x-axis. So here, if we've got this function from a to b, I've shaded in the area here. Now, for those of you who did the homework, you would have noticed that one of the questions gave a negative area. Now, that's a bit odd, getting a negative area, so what does that mean? In terms of the area problem, a negative area or a signed area is just a way of telling us if the area is either above the x-axis or below the x-axis. So here we see these red parts are above the x-axis, so we regard those as having positive area. This green part lies below the x-axis, so we say that it has negative area. Okay, so the area is still positive, we just give it a negative sign if it is below the x-axis. Okay, so the red parts that has positive area, let's put that in red. So the red parts that has positive area, and then these green parts here that has negative area. Okay, then that other part over there, that will also be positive. Now, if we're finding the total area, we're adding up all the areas. So these two parts are going to add positively to the area, which is going to make it increase. This negative part is negative, so it's going to make the net area decrease. Okay, so we say that the net area is the sum of the positive parts and the negative parts. Okay, so if the negative part over here in green is larger than the positive parts in red, then the net area or the total area will have a negative sign. Okay, because it's more below the x-axis than above. If there's more positive part than negative part, then we get a positive area. If the red part and the green parts are equal, then the net area will be 0, right? Because it's equal and opposites. If we add it together, we get a 0 area. It doesn't mean that the area is 0, it means that the net area is 0. So equal parts positive to negative. Okay, so a quick recap on what we did. So to find this area, we found this value delta x, and that was b minus a over n, where b minus a, that's the width of the interval that we're looking at. Once we have that, we can find xi, which is the x value at the base of the rth rectangle. So that's going to be a plus I delta x. Remember that I was our steps. So when I was 0, we're at the beginning, and then we made those integer steps going through all the rectangles. Okay, then we calculate f of xr. That is the height of that particular rectangle. Okay, so we've got the width of the rectangle, we've got the height of the rectangle. We can then find the area, or the net area. So that's going to be the limit as n goes to infinity, where we have more and more rectangles to make this more and more accurate. Then we have the sum from I equals 1 to n. F of xr, that's the height of the rectangle. Delta x, that's the width of the rectangle. You multiply them, you get the area. You sum all of them up, you get the total area. Okay. A few students came to me with their homework. Some left out this delta x. If you leave out the delta x, you're going to get an answer of infinity, because this delta x here provides this 1 over n at the bottom that allows it to converge to a finite value when you take the limit. If you don't put the delta x, you're not going to get a finite answer. Okay, so when doing these problems, if you do see an infinite answer, check that you do have this delta x here. Okay, you might have left it out. Okay, so always check that you include this. Okay, so that is the net area, and we did some examples on that. Okay, we'll do a few more examples today, but I just want to introduce a new notation for this. Okay, so here we called it the net area because we represent this in terms of pictures. So we've got this picture in our minds, and that area we visualize as the net area. Okay, now we're going to introduce a new notation. So we're going to forget about this area representation of it and think of this as something else. Now you can always do this in terms of areas, that's how it's defined. However, with this new way, we're just going to extend it a little bit. Okay, we're going to move away from these area pictures. Okay, and this new notation, or this new way of looking at it, is called the definite integral. The definite integral. Okay, so like I said in the previous lecture, calculus is made up of differential calculus, where we do all the derivatives. It's also made up of integral calculus, which we're doing here. And then this is one of those parts. Okay, so the definite integral, that is just another way of writing down the area from A to B. Okay, so it's just another way of writing that down. It's nothing too crazy. Later on, we'll see that there's something called the indefinite integral, and that is related to the antiderivatives that we looked at previously. Okay, so all of this differential calculus and integral calculus, it's all related, but we're just going to look at it in chunks for now. Okay, then maybe not this week, maybe next week, we will look at the fundamental theorem of calculus, and that relates everything together. Okay, so for now, just think of it as little bits together, and then we'll put it all together later on. Okay, so what is this definite integral? It's just another way of writing out this limit over here. So instead of writing the sum, okay, the big capital sigma for sum, okay, so that's just Greek for S. Instead of writing that kind of S, we write it a bit differently. We write it like that. Okay, so it's like an elongated S, just for sum. Like here we had the sigma, the Greek letter S for sum. Here we've got a elongated S. Okay, next with the notation, these bounds, so the lower bound A and the upper bound B, okay, those were the bounds for the area interval. Here we call them the bounds of integration. Okay, so it's just a renaming. So at the bottom we put A because that is the starting point for the area, and then at the top we put B, that is the ending point for the area. Okay, we call that the bounds of integration. Then inside here we put f of x, that is the function that we're integrating, as it's called, but that is just this function here under which we find the area. Okay, so again, it's just a bit of notation here. Okay, so that's the function. We call this the integrand. Okay, so previously we just said it was the graph under which we wanted to find the area. Now we're going to call it the integrand. And then this delta x, instead of writing the Greek delta, we're going to replace it with a d. So it will be dx. Okay, we call that the differential. Okay, so you've seen that before. When we did those volume approximations, we found the differential dv. Here, it's the same thing. Okay, so it means a small change. So when we did the volume approximations, we calculated the dv, and that was the small change in the volume. Here, this dx means a small change in x. Exactly the same meaning, we just write it like that. Okay, so this is just a notation. So this, if we want to calculate this, this is equal to the limit as n goes to infinity, the sum I equals 1 to n, f of xr delta x. Okay, so later on we'll see that there are tricks to find this quite easily without doing this whole limit. We're going to look at that on Wednesday. But for now, and for the tutorials that you have for this week, whenever you see this, okay, this definite integral, or if the question says evaluate the definite integral, or find the area using the definite integral, we're going to use this definition here. Okay. Later on, we'll see there's a much easier way of calculating that, but we'll save that for later. Okay, we'll do the hard work now, and then the easy work later. And again, this is just a definition. This is exactly what we saw before. Okay, so there's nothing new. We're just writing it differently. Okay, but from now on, instead of writing this limit every time we want to calculate the area, we're going to use this new notation over here, okay, called the definite integral. So we got the curly s, the lower bound, upper bound. Together, they form the bounds of integration. Inside, we've got the integrand, and this dx we call the differential. Okay, just a few words to keep in mind. Okay, let's have a look at some more examples, but instead of looking at it in terms of areas, we're going to look at it in terms of these definite integrals. Okay, but you can draw the picture, you can think of it in terms of areas, but for now we're going to start to move away from that. Okay, so some examples. Okay, so evaluating definite integrals. Okay, and just from the definition, using the limit of a Riemann sum. Okay, so definite integrals, limit of a Riemann sum, those are the key words you should keep in mind. Later on, we will evaluate these with a couple tricks, and we will move away from this limit of a Riemann sum. But if you ever get a definite integral, you should know that you can always go back to this definition. Okay, so number one. So we have the integral, so this is how we say these things. The integral from 0 to 2 of x squared plus x dx. Okay, so that's just how we say these things. Now, there's no mention of areas, there's no mention of intervals or anything like that. I just read it as is. Okay, from this notation, we need to figure out what those should be. Okay, so from here, we see that the a value is 0 because it's our lower bound. Okay, so we just read it off from this notation here. So a must be 0. Then the upper bound is 2, so that means our b is 2. The inside part, or the integrand, that's our function. So we know that f of x is equal to x squared plus x. Okay, so the function's not written explicitly down, but we know that this inside part here, that's going to be the function. Okay, now that's the new notation on the left here. This stuff on the right, we know how to work with that. We know if we have a and b and the function, we can then calculate it from the limit. So let's do that. So this is equal to the limit as n goes to infinity, the sum I equals 1 to n, f of x are delta x. Okay, that's just the definition. We can use that. Now we need to calculate what these things are. So delta x, what's that going to be? That's going to be b minus a over n. So delta x, that will be 2 minus 0, that's just 2 over n. Okay, what about our xr? We need to know that. That's going to be a plus I delta x. Our a is 0, so it's quite easy. It's just going to be 2I over n. Okay, what about f of xr? So we take our xr, we put it into f of x, and we get f of xr. So that's going to be this thing squared. So it will be 4r squared over n squared, and then plus x or plus xr, so plus 2I over n. Okay, please make sure you double check that and triple check that. If you get this f of xi wrong, then everything else below that is also wrong. Okay, so please double check and triple check that your f of xi is correct. Okay, now let's put everything together. So the limit, that stays. So we have the limit as n goes to infinity, the sum from I equals 1 to n. F of xi, we calculated that and we checked that, hopefully. So it will be 4r squared over n squared plus 2r, let's write that a bit better, 2I over n. Okay, and please remember your delta x. If you forget your delta x, you're going to get infinity as your answer, which is wrong. Delta x is 2 over n. Okay, now all we need to do is distribute the delta x inside, take out the constants from the sum, replace the sums with the closed form expressions, we did that last time, and then take the limit. Okay, so first step, distribute. So we're going to have the limit as n goes to infinity, the sum from I equals 1 to n. Okay, we distribute now, so 4 times 2, that will be 8, so we have 8r squared over n cubed. When you're distributing, please double check and triple check that you're multiplying these n's correctly. If you've got a 2 over n on the outside, and you've got this n squared on the inside, when you multiply through, it will be an n cubed. Okay, a quick way to check that you've done this correctly is if you've got an r squared at the top, you should have an n cubed at the bottom. If you have an I at the top, you have an n squared at the bottom. Whatever the power is at the top, it should be less than the power at the bottom. Okay, so we've got an r squared at the top, got an n cubed at the bottom, that should be right. Plus, and then the 2 and the 2, that will be 4i over n squared. Again, the power at the top is a 1, the power at the bottom is a 2, so that should be fine. If you have r squared over n squared, it's wrong. If you have r cubed over n cubed, again, you've done something wrong. Go back and check. Okay, now the r terms, that's what's important. We're going to leave that in the sum. The 8, the 4, n cubed, n squared, those are all constants. We can take that out of the sum. So this will be the limit as n goes to infinity. 8 over n cubed, all constants. We can take it out. Don't have to worry about that. Then we have the sum, I equals 1 to n, r squared. So you should only have something like that for your sum. There shouldn't be any 8's inside. There shouldn't be any n's inside. It's the sum from I equals 1 to n, r squared. That's it. Plus, and then the 4 and the n squared we can take out. So it will be 4 over n squared. The sum, I equals 1 to n, just r. If you have anything else inside, it just confuses things. And it's more likely that you're going to make a mistake. So here, we've got the sigma notation here, only r squared, nothing else. This one over here, only I, nothing else. Okay, now we can do the replacements. So we know the sum of 1 up to n, that's going to be n. The sum of I, that's going to be n plus 1 over 2. The sum of r squared, did anyone look that up? Okay, everyone knows what that is. Okay, good. And then the sum of r cubed, if you forget what that one is, it's the sum of I and then all of it squared. Okay, so quite easy to remember. So it's basically just the sum of I and the sum of r squared. Okay, because we know the r cubed, you just put in the I one and you square everything and you got it. Okay, so this will be the limits as n goes to infinity, 8 over n cubed, n plus 1, 2n plus 1, all over 6. Okay. Okay, if you don't have this written down with those other ones, please write them so you have those written down somewhere. Okay. Especially when you're doing the tutorials, it's nice to have a little reference on the side. Okay, then we have 4 over n squared, the sum of I, n plus 1 over 2. Okay. Once we have this, the next step is to expand everything out, simplify as much as possible, so that when we eventually take this limit, it's quite easy to do. If we were to take the limit now, we've got infinities at the top, infinities at the bottom. It's just a mess. Let's simplify first. So here we get the limit as n goes to infinity. 8 over 6, we can take that out. We don't want that to bother us. N at the top, n cubed at the bottom. That's going to result with an n squared at the bottom. So let's leave this as n plus 1, 2n plus 1 over n squared. Okay, a little bit better. Please don't try to do everything on one line, okay, unless you're comfortable with that. If you need to do multiple lines with small steps on each line, please do that. Okay. If you do multiple steps on each line, it saves you trouble with making mistakes. It also makes it easier for me to find part marks. If you do everything on one line and you get it all wrong, not much I can do with part marks. If you show steps one by one and you get the last step wrong, all the previous steps you can get marks for that. Okay, so just think about that. Okay, plus 4 over 2, that will be a 2. N at the top, n squared at the bottom. We're left with an n at the bottom, so it will be n plus 1 over n. Okay. Now, most of these problems will have the same procedure. So, this n at the top, n squared at the bottom, you're going to be cancelling things. Same thing with here, n at the top, n cubed at the bottom, you're going to be cancelling things. So if you finish the tutorials, you get it all right, that's probably enough practice that you need. Okay, but please just do those tutorial problems to get practice with this algebra here. Okay, especially in a test situation, you're trying to expand this out, you're doing the limits, you get all confused and so on. It's easy to make mistakes. If you do a lot of practice beforehand, you're going to fly through it. Okay, so now we have the limits as n goes to infinity, 8 over 6, and now I saved this top one for this line, so expanding this out, we're going to get 2n squared plus 3n plus 1, all over n squared. Plus 2, here we can already simplify a bit more, n over n, that's going to be a 1, 1 over n, that's just 1 over n. Okay, so if you have a single denominator, multiple numerators, you can always separate that out. It makes taking the limit a lot easier to do. Same thing with this first term. Single denominator, multiple numerators, let's expand that out. So we have the limit as n goes to infinity, 8 over 6, 2n squared over n squared, we're left with the 2, 3n over n squared, we're left with 3 over n, 1 over n squared, we're left with 1 over n squared. Okay, now when we take the limit, it's very easy. We see that the 3 over n, that's going to go to 0. The 1 over n squared, that's going to go to 0. If we look at the previous line and we want to take the limit, that's a bit more difficult to do. So if you can simplify as much as possible, please do so. And then we have 2, 1 plus 1 over n. Now, we take the limit. Now, since we expanded everything out and simplified as much as possible, taking the limit is as easy as crossing terms out. So here, I'll just put in red, 3 over n. If n goes to infinity, the denominator goes to infinity, the fraction gets smaller and smaller, it goes to 0. 1 over n squared, same thing. Bottom goes to infinity, fraction goes to 0. Okay, again, 1 over n. Denominator goes to infinity, fraction goes to 0. Okay, very, very easy to take the limit. Okay, but this is only because we separated this out and put it as individual terms. So, what are we left with? We've got the 8 over 6. The first bracket, we're left with the 2. The second bracket, we're left with the 1. So we have the limits as n goes to infinity. 8 over 6 times 2, that's left over, and then we just have a 2 there. So we can drop the limit now. Okay, so we did all the cancellation, there's no more n terms, so this limit we can now drop. Okay, so this is going to be 8 times 2 over 6, so 16 over 6 plus 2. You can simplify that as well. You do have your calculators, so this last step is quite easy. Once you've done this limit process, the rest is just some arithmetic stuff. Okay, so you can simplify that, but that's the main part is this previous bit, the substitution and taking the limit. That's where all the marks should be. Okay, any questions on that? Okay, let's have a look at another example. So number 2. So we have the integral from 0 to 2, x cubed plus 1 dx. Okay, again, there's no mention of any areas. We just have this thing here called a definite integral. From this definite integral, we need to get our a value, our b value, our function, and then we can use the definition. Okay, what's our a value? Good. B value. And our function. Good. Whatever's inside there, we call that the integrand. That is our function. So I'm not going to write f of x or anything like that. You're just going to get this as is. You need to identify what f of x should be. Okay, from all of this, we can then calculate what we need. That's going to be the delta x, the xr, and the f of xr. So, delta x, that's b minus a over n. So 2 minus 0 over n, that's just 2 over n. Okay, next, xr. That's going to be a plus r delta x. Our a is 0, so that's pretty easy to do. It will just be 2I over n. F of xr, we take this xr value, we put it into f of x, and we get our f of xr. So it will be 2 cubed, so 8I cubed over n cubed, and the 1 that stays. Okay. Now we can use the definition of this definite integral to evaluate this. So this will then be the limit as n goes to infinity. Then we have our sum from 1 to n. F of xr, we know what that is. And delta x, don't forget that, that's the 2 over n. Okay, so please remember your delta x on the outside there. Okay, now we distribute inside and check our powers of the numerator and denominator. Remember, if you have r squared over r squared, you've done something wrong. If you have r cubed over n cubed, again, you've done something wrong there. So we have the limits, n goes to infinity, the sum from I equals 1 to n, 8 times 2, that will be 16r cubed, and then we'll have n to the 4. So, quick check. We've got r cubed at the top, n to the 4 at the bottom. That should be fine. Plus 2 over n. Okay. Now we've got these two parts. We can separate it out, take all the constants out, and then do those replacements. So this will be the limits as n goes to infinity. The 16 and the n to the 4, those are all constants. We can take them out. And then we're left with the sum, I equals 1 to n, I cubed, 2 over n, we can take that out. And then we have the sum, I equals 1 to n of just 1. Okay, so we've got these two sums. The one is the r cubed one, and the other one is just the sum of 1s. We can make the replacement, expand out, simplify, take the limit. Okay, so this will be the limit as n goes to infinity, 16 over n to the 4. Again, if you ever forget what the r cubed one is, just remember back with the one with the r. That's going to be n plus 1 over 2, but we need to square everything. Okay, very easy to remember. Plus 2 over n, and then 1 plus 1 plus 1. If you have n of those, that's just n. Okay, again, this is quite messy. We've got all of the stuff inside. We've got it squared, n to the 4 at the bottom. We take it step by step. So this will be the limit as n goes to infinity. Let's try to deal with the constants first. We've got the 16 at the top. 2 squared will be 4. So 16 over 4, that will be 4. We can put that 4 over n to the 4. Now inside, we've got this n squared, and then the n plus 1 all squared. So it's going to be n squared and n plus 1 squared. Remember your exponent distribution. If you have a plus b, all of that squared, it will be a squared, b squared. Okay, so n squared, and then n plus 1 all squared. Please make sure that you put the square on both of them. Don't leave out one. 2 over n times n, that's just going to be 2. That's quite easy to do. Okay, now we simplify as much as possible. Here we've got an n squared at the top. We've got an n to the 4 at the bottom. We can cancel a 2 at the top and the bottom. So we're just left with an n squared at the bottom. So this will be the limit as n goes to infinity. We have a 4, n plus 1 squared over n squared. Okay, and then the 2, we just put the plus 2. Please don't forget any constants from line to line. So here we've got this plus 2, we've simplified. Just because we've got this other stuff to worry about, don't forget the 2. That needs to carry on down. Okay, I see that's quite a common mistake. When going from line to line, students leave out those constants there. Okay, please just make a note of that. Okay, so this will be the limits as n goes to infinity. Still got the 4. N plus 1 squared, we can expand that out. N squared plus 2n plus 1 over n squared. Again, plus 2, don't forget that. Okay, single denominator, multiple numerators, we can separate it out. So this will be the limit as n goes to infinity. We still got the 4, n squared over n squared, that's a 1, 2n over n squared, that's a 2 over n, 1 over n squared, that's 1 over n squared. And again, plus 2, don't forget that. Now we can take the limit. Again, yeah. Sorry? Yep. Yep, which parts? Here. Yep. So we had 4 over n to the 4, and then an n squared. So it was n squared at the top, n to the 4 at the bottom. So then that simplifies to 1 over n squared. Yeah, so this bit, let's just do that on the side. So here we have n squared over n to the 4, 2 at the top, 4 at the bottom, so that will be 1 over n squared. Yeah, exponent simplification. If I don't see your hand up, please just shout out. Okay. Okay, now again taking the limit, that's as easy as just crossing out terms. We've got 2 over n, that goes, 1 over n squared, that goes. Right, just cross it out. Okay, so anything with an n at the bottom and only an n at the bottom, like the n and the n squared and so on, that just goes to 0. If you ever get an n at the top, so if this was something like n, that's wrong. You've made a mistake somewhere with your simplification. You should never ever have n like this. Okay, it should always be something over n squared, something over n cubed. It should always be in the bottom, never like this. Okay, so please just make a note of that there. Okay, so let's put that back as a 1. Okay, so all of this, that should be in the denominator, so that when we take the limit, they go to 0. Okay, so here we can now drop the limit. We've done all of that work. So we're left with the 4 and a 2. So 4 plus 2, that will just be 6. Okay, so your very last bit over here, that will be 1 mark. Okay, just to get your final answer. The rest of the marking, that will be over here. So let me just show you for reference. So the top bit, finding all your values there. Okay, this bit over here, that's important. Okay, that bit's important. Okay, substituting, that's important. Simplifying everything and taking the limit, that's important. And then your final answer, that's just going to be 1. Okay, so that's roughly how the part marking will go. Okay, so finding those initial things, substituting, working with those sums, expanding and simplifying, and then the final answer, that will be 1. Okay, so if you do make a mistake somewhere here, then you'll lose that mark, and then you'll lose this mark here. Okay, so just check as you go line by line. All right, any questions on this one? Okay, so exactly the same method as what we did last time with finding the area. It's just with these ones now, we call it definite integrals. Okay, so it's just a renaming of what we've seen before. Okay, so for next time, we're going to look at the different properties of this. So this definite integral, remember, it's defined in terms of the sum. So properties that we have for sums will move over to properties of definite integrals. So if you ever writing out your definite integral and you forget the properties, think back to your properties of the sum. So you can take out constants, you can separate sums, and so on. Those properties will carry over. And there's a few more as well. Okay, so I'll just list out a few with a bit of homework, and then we'll do the rest of it later. Okay, so some first properties. Okay, so these will just be a few properties here. So the homework will be trying to prove them based on the definition. So we know that the definite integrals come from a sum. You know the sum properties, so use the sum properties to prove these properties. Okay, so number one is if we have the integral from a to b of f of x plus or minus g of x dx, then this is equal to the integral from a to b f of x dx plus the integral from a to b g of x dx. Okay, so before, when we had the sum, if we have the sum from I equals 1 to n, and we've got the parts, so here, let's just go back here. So we had the single sum. We had the single sum over here, and we used the properties of the sum to split it into two sums. Right? That's just your sigma notation properties. So here we could split it into two parts. So if we look at these properties, if we have f of x plus g of x, we should be able to split these into two parts as well. Okay. So you can try and prove this from that sum definition. Okay, so that's the first one. Number two, if we have the integral from a to b of some constant k times f of x dx. This k is a constant. If we go back here to how we used the sums, see, we had 16 over n to the 4. That was a constant. We could take that out. 2 over n, that was a constant. We could take it out. Okay, so this property of taking constants out of the sum, that carries over to these properties of definite integrals. So this k we can also take out. Okay, so these two are directly from the sigma notation sum definition. Okay, so I'll leave that for homework so you can prove these two. So these are straight from the sums, right? There's nothing new here. In the next lecture, we'll look at the other properties and how we use those properties to evaluate this without using the limit definition. Okay, so just a note, the tutorial, you using the limit definition. Next week, we're going to use these nice properties. Okay, so please do not do the tutorial using these rules here. Okay, you have to use the limit definition that we looked at last week and today. Okay, and then this homework that will be due Wednesday when I see you again. Okay, the compulsory homework and tutorials will continue as long as you're still failing the test and the quizzes. Okay, so far I've got a few students that are getting 80s, and they're probably going to get 80s for the semester. That's really nice to see. But the rest of the class, we need to move you up. Okay, so those that are on 50s, we need to move you to 60s. Those that are below 50s, we need to move you up to 50s. Okay, and the only way that that's going to happen is if you do this work. Right, just reading the notes and listening to me talk, that's not going to do anything for you. Okay, you need to put pen to paper and do the work. Okay, so maths is not a you need to participate, right? It's not a spectator sport. Okay, regarding students coming to my office, so far just a few students have been coming to ask questions. There's around 70 or so of you. I expected a lot more students to come with questions. Okay, considering the quiz on Thursday and how badly that went, I really do expect more students asking for help. Okay, I'm in my office. If I'm not there, you can send me an email and I can come and help you out. But you have to ask questions. If you remain quiet, you're just going to get it wrong for the next test. Okay, please, I'm here to help. Email me, email the tutors, come to my office, whatever you need to do to move up. Okay, I'll see you Wednesday.